Hi, good afternoon, everyone. We just started the webinar, but I'll just give it about a few seconds to let everyone stream in. Okay, some just ground rules. You may ask questions at any time through the Q&A box located at the bottom, or the chat box. I will be monitoring these channels to make sure that there's any questions, and then I will tell Scott that to answer the questions. Otherwise, if you would like to speak, if you could raise your hands, and then when I get round to it, I will let you have the mic. Okay. So good afternoon, everyone. Thank you for joining us and spending your valuable time this afternoon to hear Scott speak about oil-free compressors. Just a little disclaimer here: by hosting this webinar, it does not represent an endorsement of the product by ASHRAE. This seminar is organized for the benefit of members so that they are aware of what is happening in the refrigeration space. Okay, now a bit about the speaker. Scott is one of the pioneers in the creation of the oil-free compressors at Danfoss. The presentation will cover different types of oil-free compressors available in the market, as well as why oil-free technology is critical in improving system efficiency. I remember some 15 years, 20 years ago, I actually reported to Scott for a short period of time, and we were working in the same office. So there was a lot of talk about turbocore, but at that time it was still the conceptualization phase. It's great to see a product that I heard of that so far back then, and then now being commercialized at such a huge extent. Anyway, Scott Moorhouse is the Asia Marketing and Sales Director for Danfoss Turbocore Compressors, a division of Danfoss. He has spent 35 years in the HVAC industry in various roles and responsibilities in application engineering and marketing. He has been with Danfoss for the past 25 years. Scott has degrees from Swinburne University, Melbourne, ASHRAE Business College, England, and Henley Business College, England, where he pursued marketing and management. He's a regular speaker in industrial forums in Asia. Scott is currently based in Melbourne after relocation from Singapore, where he resided for 8 years. It is out of Singapore where he supported major OEMs in the Asia region with their HVAC application engineering needs. Without further ado, I'll hand it over to Scott for his presentation. Thank you.
Okay, thank you, Victor, for your kind introduction. Thank you for giving an opportunity to present this technology. So the centrifugal market has come a long way since the first introduction to field assembled chillers, and the first one was done by Willis Carrier. By the 80s, we were looking at the more modern refrigerants and factory assembled machines that we can still see in plant rooms today. And then with the evolution of oil-free technology, high speed and intelligent low GWP compressors, the market has had huge advancements in the past 15 years, 20 years.
Scott,
so there are a number of types.
Sorry, Scott, are you changing the screen? Because my screen shows that you're still on the introduction page.
Yes, I am changing the screen. Isn't it changing?
No, it's not on mine.
What do you see now?
Now I see oil-free bearings for centrifugal compressors.
Okay, I'm going to have to present in this mode then.
Okay, if you could put it full screen as well, that would be helpful.
I can, but I don't. Let me see if you can see the screen change. Can you see the screen change?
No, I didn't. Okay, never mind. It's okay then.
Okay, so we'll have to do it in this format. I apologise. I'm not sure what's the problem. So as we said, the Willis Carrier was the first field assembled chiller in the early 1900s. And then by the 80s, the mid 1980s, we were looking at factory assembled modern refrigerants on centrifugal technology. And then in 2003, there was a big breakthrough with high speed, high efficiency, intelligent low GWP compressors, which has really taken the market and changed the chiller market forever. There are a number of types. There are a number of types of oil-free applications that we can see in the industry today. So, in a very quick overview of different types of technology, we have foil bearing technology, or some people call it air bearings or gas bearing. There are a number of different generations of this bearing, and they are very popular in the aviation industry and used for years. There are some limitations on these bearings. One of the limitations is the weight of the shaft or the capacity of the compressor. So the delta P, or the difference between the high side and low side of the refrigeration system, creates the to lift the shaft. So if the shaft is too heavy, we won't have enough pressure ratio to lift the shaft. So there is some limitations. Also, on every startup, we actually start on the bearing. So the bearings do have a limitation on how many start and stops they can have in a lifetime. The next type of oil-free application is a ceramic bearing. And the ceramic bearing uses liquid refrigerant, which is pumped onto the bearings to keep the bearings cool. There are also limitations on these bearings because because of the liquid being pumped onto the bearings and the heat generated by the bearings, we can only relatively use low speed machines or low speed application on these type of bearings. And so in today's market, they are only used on negative pressure machines, or R1233 machines today. And then there's the magnetic bearing. So 98% of oil-free chillers are using magnetic bearings today, with over 70 to about 80,000 compressors in the field running today on magnetic bearings. So the oil-free market today, most manufacturers and most compressor manufacturers and chiller manufacturers are investing heavily in some type of oil-free compressor. So if we start from the top left and work our way across and then across, so we have a company in Korea called MagPlus. They have a oil-free compressor. Hanbal also have magnetic bearings. Train have launched their own magnetic bearing. Dakin have launched their own magnetic bearing compressor, the WME chiller. Train have magnetic and also ceramic on R1233. Gree have magnetic. Midea have a foil bearing, which they are quite rare in those capacities for what Midea are doing. York is using a magnetic single stage compressor. In Korea, we have a company developing foil bearings and limited to about 100 ton or 300 kilowatts. And they're also doing magnetic bearings as well. And then Carrier bring out the 19dB, which is an R1233 negative pressure ceramic bearing chiller. So conventional piping of a lubricated chiller versus an oil-free application. As you can see on the left, we have a quite complex setup to extract the oil from the evaporator. And on the right-hand side, the piping arrangements are extremely simple for oil-free. So it makes the piping extremely simple. This slide goes into a little bit more detail for a lubricated system. So on the left is quite a complex centrifugal machine with oil heaters, etc., making it very complex to manufacture. And on the right-hand side, also even screw lubricated machines are very complicated in retrieving the oil from the evaporator. So this is a schematic of a Carrier 23XRV, which has a lot of piping arrangements to retrieve the oil back to the compressor. On the ceramic bearings, as we explained before, we have to pump liquid onto the bearing assembly inside the compressor. And so the pump arrangements are very complex and very expensive for ceramic bearings. So it's not just as simple as running a set of ceramic ball bearings. We have to pump liquid refrigerant onto the bearing to keep them cool enough to run. And as you may understand, these low pressure machines on R1233 are very big in dimension and very heavy. So on this slide, if we have a conventional machine, if we have a magnetic bearing versus a ceramic machine, the magnetic machine is 44% less footprint, 58% less weight, and the ceramic bearing compressor weighs 3,500 kilos, where the total compressors of the same capacity on magnetic bearing only weigh 600 kilos. So significant difference when we're using these low pressure machines. So for replacement, these low pressure machines may not fit into the existing plant room. So we have to be very careful of that. One type of technology, what we call on the market, is an integrated compressor technology, where all of the components for the compressor and the speed control and the starting are assembled on the compressor. So this compressor is a two-stage centrifugal compressor, where we have suction goes through the first stage, through the volutes, into the second stage, and then out the discharge. We have an inlet guide vane. So for the majority of the loading and unloading, we use speed control. When we cannot unload the machine anymore, we will use the inlet guide vane or mechanical control to unload the compressor. But the majority is done by speed, because this is the most efficient way to unload a centrifugal compressor. In the top of the compressor is situated what we call the high power electronics, or the inverter. So in here we have what we call a soft start. We have silicon controlled rectifiers. We have an IGBT. So we go from AC coming in through a set of line reactors to reduce the harmonic. We come into the SCRs. We change from AC to DC. We put it through the IGBT, and then we come out as a high voltage AC chopped waveform to control the speed of the motor. The motor on this particular compressor is a permanent magnet. So these are the most efficient motors for high-speed applications. So there are magnets inside the shaft to create a high efficiency. On the side of the motor, on the side of the compressor, we have all our controls. So all the intelligence goes into the compressor. So on a centrifugal compressor, we have a number of different operating conditions when we're using a centrifugal compressor. And in the past, centrifugal compressors have mainly been used, or 95%, 98% of the time have been used for water-cooled applications, because the pressure ratio could not be high enough to use them for air-cooled applications. To get higher pressure ratios, we either need more impellers, so more stages of compression, or we have to have higher speed. And so with the oil-free magnetic bearing technology in the market today, we have 2 impellers and very, very high speed. So the maximum speed on these compressors are up to 45,000 RPM. There are manufacturers today working with technology of up to 200,000 RPM. But today in the market, the highest speed for a 300 kilowatt compressor is 45,000 RPM. Victor, we can do poll 2 if you like.
Poll number 2, is it?
Yeah.
Okay.
So the magnetic bearing system, the rotor shaft is held in position by permanent magnets.
I think we give them some time
continuously
to
controlled by electromagnets. So the heavy lifting is done by permanent magnets, and the electromagnets position the shaft to where we need to position it. The sensors look at the shaft over 6 million times to position the shaft correctly. And one of the key aspects of some technologies on the market is active surge control. So on conventional machines, when we look at looking at a surge condition, we monitor the operating envelope, or the map, where we are on the map, and we also look at the amps. But on magnetic bearing technology, we look at the shaft and how unstable the shaft is becoming. So the more unstable the shaft becomes, the closer we are coming to the surge line. So we have what we call active surge control.
Scott, you want me to share the results of the poll?
Yep, that'd be great.
Yeah. Okay. So yeah, most of y'all, I think the answer is, what's the answer? What is the maximum speed of a 300 kilowatt?
45.
Yes.
Yes.
So a few of y'all got 10,000, 20,000, but the correct answer is 45,000. That's where the majority got the answer. Okay, cool.
Great.
So Scott, just a quick question. So why is the market pushing for higher RPM for these magnetic bearings? Like you said, 200,000?
Usually, mainly because they want to go to smaller compressors. So there is a market demand to have smaller compressors. So compressors, oil-free magnetic compressors that can do the rooftop market in the US, that can do edge data centers, small containerized data centers. That will be a huge push in the coming years, and even go down to VRV or VRF type applications. So the smaller we go, the higher the speed we're going to have to run.
Okay, gotcha.
And
Thanks.
so if you look at it in today's market, a 300 kilowatt compressor will maximum speed will be 45,000 RPM. If you look at the equivalent compressor at 1600 kilowatts, the maximum speed may be around 18,000 RPM. So the bigger you go, the slower we go. The smaller you go, the faster we have to go. So the magnetic bearing clearances that we're looking at when we levitate the shaft. So when we levitate the shaft into midair, we're only moving the shaft a very small diameter. So we're lifting the shaft about as much as a human hair. So they're not big air gaps. So we have to control these shafts extremely accurate, because there are very small tolerances between the shaft and the touchdown bearing. And so if you can see on this slide, we have a radial bearing, a front radial bearing, a rear radial bearing, and an axial bearing. And these sensor rings look at the radial positioning of the shaft, and this front sensor ring looks at this target sleeve here at the front, and that goes back and tells the actual bearing how much power we need to put into the actual bearing. And these actual forces can be quite high. So the higher the pressure ratio, the higher the actual forces are on this rear bearing. And that's the limitation on a single-ended compressor. I won't go too far into the architecture of how the bearings work, but we take the sensor inputs and we go into what we call our bearing motor controller. That bearing motor controller gives an output to a PWM, or a pulse width modulator, telling the bearings how much 250 DC needs to go to the bearings to position the bearings. And we have multiple X, Y, and Z position sensors that we look at the shafts. So these compressors are very compact, and having an inverter on board the compressor, we need to cool a lot of the electronics, and we need to cool the IGBT, and we also need to cool the motor. So the thermal management on these compressors can become quite complex, but it is one of the keys to being so small. The compressors are extremely small. So we have solenoid valves that will pulse liquid refrigerant into these cavities. So we have an electronics cavity, which will do the inverter, and then we have a motor cavity. So each one of these valves will control that. One will do the motor and one will do the electronics. And we have a number of sensors over the motor and electronics to determine how much liquid refrigerant we need to put on to cool the electronics. Once we've gone in as liquid into two phases, it's gone through and superheated the gas, the electronics path will go back into the second stage, and the motor cooling will go back into the first stage, because it's a two-stage compressor. One question we get commonly asked in the technology is why don't we use screw technology with magnetic bearings? And the answer really is that we have two types of technology in compressors. We have positive displacement compressors, which are screw, scroll, piston, and rotary. And then we have centrifugal. And centrifugal uses kinetic energy to increase the pressure, where positive displacement physically takes the gas and squeezes it through a set of scroll plates or through a piston or through a rotor on a screw, that physically takes the gas. And these forces on the bearings, when we're physically squeezing the gas, are extremely high, and magnetic forces could not handle these stresses. On a centrifugal, we just spin the impeller extremely fast and we induce the gas and then create a pressure difference using kinetic energy. So some of the common applications we do with oil-free are air-cooled application, water-cooled application, and evaporative condensing application. Evaporative condenser, not so, doesn't add any value in Singapore, but in some of the drier climates, evaporative condensing chillers do create a very big value. 98% of oil-free applications are flooded vessels. So there's very, very little DX or direct expansion work in the field with oil-free compressors. So Victor, we can probably do poll 1 now. Victor?
Yeah, just launched it.
Okay, thanks. Okay, so one of the benefits of using oil-free is that we have no oil degradation. So in a flooded evaporator, the oil from a lubricated compressor will sit in the evaporator until they return it to the compressor. But there is always an overfeed of oil over a period of time. And the oil that sits on the copper tubes acts as an insulation. And for many years in our industry, we were quite unclear on how much impact. So we really never used the oil degradation on our return on investment calculations. And this was mainly due to that we didn't have a lot of studies. But this has changed now. There is a number of studies out in our industry today that give some very accurate numbers on oil degradation, how long it takes and how much impact we have on the energy efficiency or the return on investment for these machines. So the industry accepts performance loss over time. The industry in the past really didn't recognize it, but now they accept that there is oil degradation in machines. So we can consider about 10% degradation or performance loss after 5 years, and 20% of degradation over a 10-year operation. And with all these reports on the market today, it's considered that the waterside fouling accounts for 4.8% of that derating, which will be common on an oil-free machine and a lubricated machine. The refrigerant side fouling accounts for 5.7% of the fouling over that period of time. And the compressor degradation and other factors account for 8.7%. So this can be rotor wear on a screw if the bearings haven't been replaced at an acceptable time, etc. So these are the sort of numbers that we're putting down for degradation over a period of time. Some of these results have come from a very good case study by the Chiang Mai University, where they studied 24 buildings, 36 chillers, 26 centrifugals, and 10 screws, and did the comparison of the performance versus the rated performance when they were originally purchased. So it's an extremely good study and very well executed study.
Scott, I'll share
the
the
other
results.
8.7% wear that we talk about was can be due to mechanical losses. There was a study done in the US, a Hershey factory in the US, and a television studio in Melbourne, where some compressors were taken off the site that have been running for over 10 years and taken back to the factory where they were produced. And a performance test was done to see if they'd lost any performance at all over that 10 years. And the results were that they did not lose performance over the 10 years because the magnetic bearings don't have any mechanical touching, so there is no wear inside the compression area. So the result was zero loss of performance in that case study. Also, with smaller high-speed machines, we can, a lot of applications are using multiple compressors. So this is a key in redundancy for certain applications. And also meaning we can unload the compressor significantly more than a large single compressor machine. So we have a big advantage with multiple compressors. Also, when we levitate a shaft and we run off, we're not generating any massive amounts of heat into the system. So we can get our compressors off and running in 30 seconds if we have a power outage. This is a key advantage in mission critical sites such as data centers. Also, the fact that we don't have any mechanical touching of bearings means we don't have any vibration. If we don't have any vibration, then we can have a very low sound. So the pumps are louder than the compressors in the plant rooms when you're using magnetic bearings. And we can have as low as 77 dB at 1 meter for a magnetic bearing compressor. Also, because we're just levitating the shaft and spinning the compressor up to speed, we only need 2 amps to get the compressor going and start spinning off. Compared that with a conventional screw machine at the same capacity, where we'd be using about 500 or 600 amps to get a conventional screw up and started. So we don't have any high inrush current affecting the motor windings. Installations, because it's oil-free, it's a very easy knockdown process, and so we have some very reassemble the machine in the plant room, and even going up goods lifts on some of the smaller installations, so saving the money a lot on cranes. The data center market has changed significantly over the past 5 and 10 years, mainly over the last 5 years, and we're seeing higher and higher SST, or leaving water temperatures. And some of the conventional compressors are struggling with these high leaving water temperatures. So magnetic bearings can withstand these high leaving water conditions quite easily, and they actually have specific compressors built for data centers or high SST operation, saturated suction temperatures. Also, we can also run at very low pressure ratios. So we can take advantage of the very low temperatures at night, where other machines or other compressors rely on a pressure ratio for their oil management, but we can reduce our pressure ratios extremely low and take advantage of the more efficient area where we run at. When we run them extremely low, we do need to add a refrigerant, a small refrigerant pump, to boost the motor cooling and the inverter cooling on this. And there was a case, a data center done in Melbourne, where there was some existing chillers that were running, and we looked at the performance of these machines. And then as an aftermarket product, a low lift system was fitted to these machines. And we took a 5-star data center, and we had significant improvements of up to 30% when running in low ambience. These chillers there was a number of chillers, about 12 chillers with about 1200 kilowatt refrigeration. And we went to COPs as high as 19 on that application. So even though the data center was already a 5-star data center, we improved the chiller performance by 30% in certain ambient conditions. As we said before, a single-ended compressor has limitations on high pressure lifts or high temperature applications. So to limit the actual force, compressor manufacturers have gone to back-to-back or double-ended compressors. So they put the impellers on each side of the shaft, and this in turn balances the actual forces. So as the pressure ratio goes up, the two impellers, or the double-ended impellers, actually balance each other out, and so we don't have very high actual forces. So that means we can even go to higher pressure ratios than we first started with. So these pressure ratios, we can go up to about 6.2 pressure ratios, which means we can do air-cooled application at 58 degrees ambient. And we can go down to minus 25. These types of ambience, or SDTs and SSTs, are unheard of in the centrifugal industry prior to these high-speed magnetic bearings. So a very, very wide operating envelope for a wide for a lot of applications. And so I think that's about it, Victor.
Yeah, I'll probably go through the answers for the second poll question that was launched. Can magnetic bearings be used on screw compressors? What was the answer, Scott?
No, they can't. They can't be used.
Yeah, that's where the majority, 65% of you all got it correct. Some of you answered yes, and some of you only on rotary screw compressors, but the majority, congratulations.
There was one more poll question that I didn't actually get to, Victor. But on an oil-free machine, there's a question comes very often. What is the difference on a magnetic compressor if we use R134A or R1234ZE? And the question comes up very often because some people want to retrofit these in the field, etc. And we know that we lose approximately 25% capacity when we go to HFO. But the mechanical difference on a compressor, on a magnetic compressor, there is no mechanical difference. It is only software. This is depending on the compressor manufacturer, but a lot of the compressor manufacturers just take an R134A compressor and use it on HFO and just change the software or the operating map of where the compressor will run.
But you will lose about 25% capacity, is it?
Yeah, you lose 25% capacity.
Okay, cool. While any questions from the participants, if you all would like to put it in the Q&A box and the chat box, I'm monitoring it, or if you would like to raise your hands, I will allow you the mic. In the meantime, maybe I have some questions of my own. Why was there no DX set up for magnetic bearings?
No direct expansion?
Yeah, correct. Is there, you mentioned that there's no DX applications for?
Usually because magnetic bearings are a premium product, and for a premium product, they want a premium efficiency. And direct expansion, as you know, has a fairly high approach. On flooded machines, we can get down to half a degree approach on the chiller vessels, so making them extremely efficient compared to direct expansion. So yeah, the majority of manufacturers just do flooded air cooled or flooded water cooled. But as these compressors, you know, the high lift compressors come out, the applications are really changing. 10 years ago, 90% of our work was commercial building. Now, commercial buildings are probably down to about 20%, 30% of our work. So data centers is a huge market for us. The mining industry. So we are moving away from just commercial buildings and getting into different applications.
So you guys are going into mining more extreme conditions, situations, applications, is it?
Yeah, we do a lot.
Okay.
We do a lot of mining here in Australia. So they have to air condition the mines to keep the people cool down in the mines.
Okay. And then another question is, why do conventional compressors struggle with high SST?
Because a positive displacement compressor is a fixed pressure ratio. So if you take up your SST, your SDT goes with it.
Okay. And
you have quite a small band on an SDT because you start to have degradation on oil, or your oil starts to break down at a set SDT.
Okay.
So,
I see.
And for oil-free, we had different problems that we had to face. As your SST goes up, you don't have as much cooling for the electronics, because instead of cooling your electronics at 7 degrees saturated, now you're trying to cool your electronics at 20 degrees saturated. So we had another bunch of problems that we had to, you know, design the compressors to handle these high SSTs.
Okay. So we have a question from the attendees. What is the lifespan of an oil-free compressor?
20 years is a designed life cycle.
Okay. Okay. Any more questions from the participants? I'll give it 30 seconds. Can oil-free compressors use natural refrigerants?
Not yet.
Okay.
Sorry.
From Peter Cheng, that was. Yep. Then 30 seconds. If there's nothing else, I will pass the mic to Mr. Yuichi, our president for ASHRAE for 2021 and 2022. Let me find his. Okay. Thanks, Scott. Really appreciate the time you took. It's late for you guys already over there. Nice meeting you as well.
Not too bad. I thank you very much for the opportunity to have a little talk about oil free.
Yeah, sure. I'll hand it over to Yuichi Takesmasa.
Yep.
He's our president for outgoing president.
Can you hear?
Yeah, we can hear you.
No video?
No video though. I don't know what you're not
okay.
sharing or wait, I'll share the video. Give me a minute. I forgot I'm new to this as well. So yeah. Move. Wait. Two panels. Okay.
Oh yeah. Panelists.
Better now? Okay.
Yeah.
Did I get you?
Hey?
No, talking to Yuichi.
Yeah, this is it. Can you hear me?
Yeah, I can hear you, but no video though. Got you.
Okay. This is Yuichi Takemasa. Yeah, thank you for your kind introduction, Victor. I'm Yuichi Takemasa, president of ASHRAE Singapore chapter in this term. And my term will end soon at the end of this month. So I'm the outgoing president. And today's webinar is the last event for me as president. And thank you, Mr. Scott Moorhouse, for giving a lecture, very insightful lecture on refrigeration. And I think you are in Melbourne, am I right?
Yes, correct. Yeah.
Thank you for attending from Melbourne. I think time difference is probably 2 hours or 2 or 3 hours.
Yeah, it's not too late here, so it's fine. I'm used to late meetings anyway.
Yeah, it should be in the evening, and thank you. And as everybody knows, that this refrigeration webinar is in commemoration of World Refrigeration Day. And World Refrigeration Day was created to raise awareness about the importance of refrigeration technologies in everyday life and raise the profile of the refrigeration, air conditioning, and heat pump sector. The day was chosen to celebrate the birth date of Lord Kelvin on 26 June, 1824. And I think today's webinar was a very suitable topic for refrigeration webinar commemorating the World Refrigeration Day. I appreciate Mr. Scott Moorhouse for your time to prepare for this webinar and also taking time to attend this webinar. And today's webinar, thank you. And today's webinar is also a new trial for ASHRAE Singapore chapter because we decided to make it open to our friends and colleagues of other chapters than Singapore in Region 13, which is Asia and South Asian countries, with 10 chapters in this area. And this is the first trial for ASHRAE Singapore chapter to do that. And I understand more than 50 people from various chapters in Region 13 attends this seminar. And I'd like to thank you for attending today's webinar. And I hope all the audience enjoy the webinar. And the webinar by Scott Moorhouse was very beneficial to those who attended this seminar. And once again, I'd like to thank the speaker, Mr. Scott Moorhouse, and wish all the participants a good evening. Thank you.
Thank you very much.
Thank you very much.
Thank you. See you guys. Take care. Bye, Scott.
Take care. Bye.
Yeah, bye.
Thank you.
Thanks.